Hello everyone, this is Rathan Babu working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics, and the topic is multi-grid methods and their usage. So here the meaning of multi-grid is the combination of two or three, or let's say more than two domains which are clubbed in a single domain. So in the previous modules or the previous lectures, we have seen about grid and grid or mesh and types of grid, and we have seen the combinations of grid. So just to recall that, so let's see what is grid actually. So grid is an entity so which is dividing the domain into subdomains. So let us consider this as 1 and 2. So this 1 is nothing but an entity which is divided into subdomains, and 2 is nothing but it's a domain, overall domain. So here the X lines, so Y lines are called grid lines. So these grid lines are dividing the domain into subdomains. So here you can see that the grid is, or the mesh is dividing the domain into subdomains. Now this is of single entity, so this is called single block. So this is called a single block. So this single block is nothing but a domain which is dividing the geometry into sub different parts, and therefore characterizing the flow, and therefore investigating the flow at each and every point. Now here, what do you mean by the multiple blocks? Multiple blocks in the sense the combination of other blocks. Let's say we attach a block here, we attach a block here, we attach a block here. So therefore when we add some other blocks to the original block, so we call it as multiple blocks. So we will see in detail what is the purpose of multiple blocks, and what is its usage for different applications. So again, to recall about different types of grids. So there are basically two types of grid or mesh. So one is called structured grid or mesh. So the other one is called unstructured. So one is called the structured mesh, other one is called unstructured mesh. So we'll see basically what is the difference between them in short. So again, let us draw some diagram. So this is for structured mesh, this is for structured mesh, and let us draw this for unstructured mesh. Okay, so for structured mesh, so even when the boundaries are regular and simple, so we can use this kind of arrangement. So whereas for unstructured mesh, so you have these cells, so which is of different shape and size. So here you can see the entity, so which is having the random nature. Okay, so here you can see in the figure 1 and 2 the difference is, so in the figure 1, so whatever the cells you are seeing, so basically this cell 1, so 1 2 3 4 5 6 7 8 9 10 11 12. So here we have 12 cells. The 12 cells are basically of either square or let's say rectangle. So basically let's call it as a quadrilateral. So these are the quad shapes. Now in the second one, which is for unstructured grid, so all the elements are of triangular shape. So here if you take a grid point, so grid point is nothing but the intersection of lines. So here if you take a grid point, so it is basically surrounded by so 4 neighboring points. So you have point here, so let's say point 1 2 3 4. So in a structured mesh, so if you see the internal grid points, so it is surrounded by neighboring 4 points. And one important and the major difference is, So no two X grid lines. So this is X grid line 1, X grid line 2, 3. So Y grid line 1, 2, let's say. So no two grid lines will meet each other. So let's say you take X grid line 1, X grid line 2, X grid line 3. So Y grid line 1, Y grid line 2. So you see at any time, so these are like railroads, whether like let's say they are parallel. So y1 and y2 they will never meet each other, and x1, x2, x3 they'll never meet each other. So this is the basic condition for the structured grid or mesh. And whereas for the unstructured grid or mesh, so what happens actually? So there are no grid lines which are parallel to each other. So they will meet each other, and they form a triangle. In the case of, so basically this is called 2D mesh. So this is called 2D mesh. So for the 2D mesh, so they form a quad, and basically these are triangular cells. So these are called the quad cells, and these are called the triangular cells. So you can see the cells, so which are found 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 cells are there. So in the 15 cells, so basically there are these are the triangular units, and the basic unit, so you can see the cell. So this is for the structured grid. For the unstructured grid, so you have the triangular. So where here you have 4 grid points, here you have 3 grid points. Okay, so that is the basic difference. So where do we use structured mesh? Where do we use unstructured mesh? So basically the structured mesh is used for simple geometries and the boundaries which are regular, and where the geometry does not have any complexities. And unstructured mesh, so basically they can adopt the geometry, and the time taken to generate mesh will be less, but the thing is more number of grid points are associated with that, and it is not simple, like when you go in terms of the coding terminology, so it is not simple to generate. But one advantage is it can be used for the complex geometries. So unstructured mesh cannot be performed for the complex geometries. Why? Because so there will be the intersection of the two grid lines. So let's say you have y1, y2, x1, x2, x3. So they will intersect with each other. So therefore that is the reason why structured mesh cannot be or may not be used. But mostly people, when they are going for the complex geometries, so they prefer for unstructured grid to save the time for generating the mesh. And if you are going with unstructured mesh, it will take time, but it will give good results with easiness. So that is the major difference. So when we see a 2D mesh, 3D mesh, so let's see the difference. So basically 2D mesh, and let's see 3D mesh. So mesh or grid, mesh or grid. So let's see, basically this is a 2D. Okay, so this is 2D mesh. Now for 3D, so what do we have actually? So when you consider 3D mesh, so this surface, every surface will be divided into subdomains. So here let's say your surface. Okay, so basically this is 3D mesh. So here for the basic difference between 2D and 3D, you can see this cell. So what we have here, it is basically called quad. Okay, so here the cell, the basic cell which we have, so here it will be 3D, so it is called hexa. Okay, so quadrilateral and hexahedral cells. So this is the basic difference between 2D and 3D mesh. Now when we go for the unstructured grid, so here let's say you have the triangular unit. So this is for unstructured grid. So let's say for 3D, so we call it as a tetrahedral. Okay, so basically this is of 3D. So this is the 2D of unstructured mesh and this is 3D of unstructured mesh. So when you see a 2D view, so basically they are called quad for structured mesh and tri, so basically triangular. These are triangular and these are tetrahedral. Tetra. So basically tetrahedral cells. So these are called tetrahedral cells and basically for structured mesh it is called hexahedral cells. So when we want to categorize the smallest basic units of the mesh for structured and unstructured grid, so in case of 2D, so this is called quad and 3D it is called hexahedral and for the 2D it is called triangular for unstructured mesh and 3D it is called tetrahedral. Okay, so with this knowledge let us see, so basically, so what is multi-block approach and how do we actually perform the multi-block, and we will see hybrid grids also. Basically, what is hybrid grid? Can we join or can we use combination of both structured and unstructured mesh? So is it possible or not? We will see. So already we have seen in the previous cases, so the previous modules, so which is of C and O grid. So let us say again the C type mesh, okay, CH combination. So you can take this as CH combination. So let us draw the airfoil again. Okay, so let's draw the airfoil again. So let's see basically what do you mean by multi-block for the airfoil. So if you see the overall or the basic simple domain, okay, so basically this is geometry and basically the domain. So there are two types of flows in CFD. One is called the internal flow, other one is called the external flow. So flows are categorized into two ways. One is internal and external flow. So when the flow is, let's say, external flow in the sense flow is passing over the geometry or over the body. So examples are like flow over aircraft, flow over wind turbine, flow over motorcycle, so flow over car, flow over truck, train. So these are the external aerodynamics. So let's say when we talk about internal aerodynamics, so flow through pipe and flow through the ventilation systems and flow through the engines, so jet engines. So these are some of the examples of internal flow aerodynamics. So for the external flow aerodynamics, so what do we have? The domain is drawn outside the geometry, so where we need to actually perform the mesh over the geometry and simulate the flow over the geometry for the external aerodynamics. Whereas for the internal aerodynamics, so what we do is like we will take the domain inside the geometry and we will perform the mesh and every other aspect inside the geometry and we will give the boundary conditions and run the simulations. So that is a basic difference. So next example, for the example we will be seeing internal dynamics after we see this C type of mesh. Okay, so if you consider, so basically this is called overall domain. Okay, so this is called overall domain. Now, so when you want to divide into multi-block, so basically this is called a single block. You can see this is of one block. Okay, so when you exclude, so when you don't like geometry is, it's a body which is placed inside the domain, but if you see the outer part, so the outer part is a single domain, single entity. Now how do we create the multi-block? So we can create the multi-block by dividing into different partitions. Now what is the purpose of multi-block is, so when you are performing a structured mesh, when the grid lines are running from one place to other place, they will not intersect with each other. So when you use multi-block, so when you don't use multi-block, what is happening is like, so when you are drawing, let's say, a grid line from this point to this point, or from here to here near to the geometry, so they may actually get uh, overlapped, or let's say they cross with the other grid line. So that may happen. So when you divide into different blocks or different subdomains, so basically in the term of technology or technicality, so we can say that it is of multi blocks. So here, let's say I am dividing here into, so, two blocks. So let's say this is block 2 and this is block 1. So initially we had only one block. So when I have drawn a line in front of the leading edge of airfoil and the trailing edge of the airfoil, so we have drawn a multi-block actually. So multi-block, in the sense, what happened, like here we have two subdomains. So initially we have only one domain. So when we have divided a partition here, so it is divided into two subdomains. Now, so is it possible to generate geometry? So we need a closed entity. So therefore what we will be doing is like, so we draw a line here. So let's say we'll draw a line here. So I'm giving an example. So basically this will come from the thickness of the airfoil. So let's start here actually. Okay. So now what happened, actually we have divided again the domain into subdomains, which had taken 4. So initially we had 1. So now this 1 is divided into totally 4 subdomains. So this is called block 1, this is called block 2, this is called block 3, this is called block 4. So basically when we have divided one domain into 4 subdomains, so we have divided one block into multi-blocks. Okay. So now what is the advantage of multi-blocks? So when we have done the multi-blocks, so if we require any special attention at the leading edge of the airfoil, let's say I want to see more about the stagnation performance of this airfoil at a different angle of attacks. So I'm very much interested what is happening at the leading edge. So in this case, so you can actually perform a special type of grid arrangement. So when you divide into specialized blocks. So let's say here I have divided into 3 and 4. So I can use more number of grid points here, or I can use more number of grid points here, and I will go for less number of grid points. Why? Because here this is not my interest. Okay, so my domain of interest or the area of interest to investigate the CFD problem is at the leading edge of the airfoil. So therefore I will perform special grid techniques to capture data very well at the leading edge of the airfoil. Okay, now when we have this multi-block, so what, like, can we use structured and unstructured mesh? So is it possible? Yes, we can do it actually. So that thing we'll be seeing for the combination of rotor and starter for next example. But for this we will see what is for the multi-block. That's it. Now, so what happened? So when we have divided into 1, 2, 3, 4 blocks, so we have created a subdomain which is with 4 surfaces. So when you want to generate a proper structured mesh, so it has to have 4 surfaces actually. Here you can see 1, 2, 3, 4. This is 1. So we have 1, 2, 3, 4 surfaces. So when you take this as one entity, okay, so from here to here, if you take this as one entity, we have 4 surfaces for block 1. So when you take block 2, here again you have 1. So from here to here you have 2. So here you have 3. Here we have 4. So basically again here you have 4 surfaces. Okay. So when you don't have, let's say, 4 surfaces, the quad element. So what happened actually? Formation of structured mesh is not possible. So when you have only 3 surfaces, or let's say more than 4 surfaces, so what happens is like the mesh can be taken mostly in terms of unstructured mesh. Okay, so that is why, so we are dividing So this airfoil geometry, so which is having a domain into subdomains, so into like 4, and which has the 4 surfaces everywhere. So if you see the domain 3, so here also you have surface 1, 2, 3, 4. Again here also you can see surface 1, 2, so 1, 2, 3, 4. Okay, so these entities will actually perform or will give us a proper structured mesh very well without any non-orthogonality. Orthogonality is nothing but making an angle 90 degrees. So properly, if you have a mesh which is making with an angle of 90 degree, so which has very orthogonal, so it won't give problems. So when it is very well non-orthogonal, so the deviation will give some non-accuracy. So we need to correct it orthogonally. So that's in terms of structured mesh. Okay. So therefore, what happens here? So when we see this division, so we can perform a proper orthogonal mesh, structured mesh. So that is why. So we are dividing into multi-blocks. So what happens actually here? So here, so we have proper structured mesh, so which is adapted to the leading edge of the airfoil. So here also you have proper structured mesh. Okay, so this is what exactly when we divide into multi-block. So here we'll have so these straight lines with the proper arrangement. Okay, so this is the example of the multi-grid. So let's see another example. So which is of a combination of rotor and let's say starter plane. So let's say we have an airfoil here vertically. So this is one thing. So let us say this is the domain of interest. Okay. So here we have this airfoil 1. So this is of airfoil 2. So in this midway passage, so let's say we want to investigate the flow performance, let's say. So what we will do actually, so we will have to create a domain, so which actually perform the simulation realistically. Okay, so this is one thing. Now let's say when we create this domain, so I will divide them into blocks. So let's say so here you can see so this is block 1, let's say, and this is block 2, so this is block 3, and remaining block 4, block 5, let's say. So when you join this as a single entity, so everywhere when you want to generate a structured mesh, so what happened actually, so you need to generate a 4 phase surfaces. Okay, so if you are not able to generate 4 phase surfaces, then you cannot generate structured mesh. Okay, so I'm talking like I'm just concentrating on to generate this structured mesh. So that's why I'm creating more and more amount of blocks and to create flow visible like flow flexibility. Okay, so using structured mesh. Now when we do this kind of arrangement, so what happened actually, block 1 2 3 4 4 5, so 5 blocks we can perform a structured mesh. But if you don't want like these multi blocks, so let's say if you are very hectic to perform the, if you get hectic to perform the structured mesh, so you can use unstructured mesh directly. So you can take this entity as one block, so even this entity as one block and other entity as another block. So directly you can generate unstructured mesh here. So you can generate unstructured mesh here. So this is an example of generating unstructured mesh. So here, what happened here in the domain 1, you have unstructured mesh. So why? Because it was very hectic. Even in the geometry 3 and 4, like domain 3 and 4 also, you can construct unstructured mesh. So since here it is regular, so you can generate a structured mesh. So here you can see that in the domain 1, I have unstructured mesh. Let's say in the domain 3, 2 also have unstructured mesh. But 4 and 5, so since the boundaries are regular, I can take structured mesh. So we have a possibility of combination of structured and unstructured mesh. So basically, these are like called hybrid heats. So basically, there you have the combination of structured and unstructured mesh. Okay, so this is these are the two types like examples. So let's see one example for the flow through pipe. So where we can see a simple example of internal geometry. So previously we have seen the external geometry, or let's say external flow. Now let's see example for the internal flow. So for the internal flow, so let's say this is my geometry. This is pipe. So this is inflow, and this one is outflow. Okay, so basically this is wall 1, so this is wall 2. Okay, so this is the 2D view of 2D view actually. So here we have 2D view. So if you want to generate a structured mesh, you can generate a structured mesh. If you want to generate unstructured mesh, you can generate unstructured mesh. But the many people will go for structured mesh when you have simple geometries. So pipe 2D pipe is a simple geometry, therefore people opt for the structured mesh. So what we do, we'll assign points. Let's say point 1, 2, 3, 4, 5, 6, 6, 7, 1, 2, 3, 4, 5, 6, 7. So along y direction. So basically along x we have taken 7 points. Here also 7 points. We'll add join. Similarly here also let us take 1 point. We'll join. So how many grid points we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, let's say. So here again I will take 1, 2 and 3. So what happened here? We have 15, 16, 17, 18, 19, 20, 21, 22. So basically grid points 1 to 22. So these are called the boundary points. Okay. So grid points. So basically 1 to 22, they are called the boundary points. So here what we do is actually, so points 1, 18, 7, 16, 15. Let's say, let me give in terms of coding terminology. So 15, 16, 17, 18 and 1. So basically these points are constituting for inlet phase. Okay. So these grid points are belonging to the inlet actually. So points 1 to, so next points 1 to 8. So they are for wall 1. Next points 9 to 15. They are for wall 2. Next points 19 to 22. So they are for outflow. Okay. So we have given the terminology of the grid points and let's say boundary points and the boundary points. So basically when we give boundary conditions, each and every grid point, so it will get those values. Let's say I am giving the initial or let's say inlet velocity as 2 meter per second. So what is the meaning is at the grid point 1, sorry, at grid point 18, 17, 16, you will have 2 meter per second. So the value of velocity at grid point 18 will be 2 meter per second. So value of velocity at 17 you will have 2 meter per second, and value at 16 you will have 2 meter per second. So when I give uniform value along the inlet, so I will have each and every grid point value as 2 meter per second. So that is the inflow. Now, so boundary condition. When I say boundary condition, so what is a boundary condition actually? So on the boundary surfaces, so we have 4 boundaries. Boundary 1, 2, 3, 4. So why? Because wall 1, wall 2, and next say inlet and outlet. So we have 4 boundaries. So for the inflow boundary conditions, we will have velocity inlet or mass flow rate inlet. So these are the boundary conditions. So already we have seen the Dirichlet boundary condition and Neumann boundary condition, and the Dirichlet boundary condition, so we'll give directly values of velocity. Let's say u is equal to 2 meter per second. For the Neumann boundary condition, we'll give velocity profile or let's say gradient. So dou u by dou x is equal to some value 0 or some kind of thing. So this is what we give for Neumann boundary condition. So this is for Dirichlet boundary condition and this is for Neumann boundary condition. So combination of Dirichlet and Neumann is called mixed boundary condition. Okay. So now, so when we give these values, so here 16, 17, 18 values 2 meter per second. So initially they will actually, before starting simulation, they will have the values, and when starting simulation they will calculate values with respect to these adjacent points. Okay. So this is what the feasibility of structured mesh we have. When you go for unstructured mesh, so the same thing will be there, but adjacent to that we'll have more number of grid points. And one more thing, so for the inlet we have given these values. For the wall, what do we give? So at this we'll give velocity as 0. So at 1, so basically from grid points 1 to 8, so you will have u velocity as 0. Here also u velocity as 0. Why? Because we call it as no slip wall boundary condition. So the meaning of no slip wall boundary condition is, so velocity at the wall is 0. Slip wall in the sense it is not equal to 0. So slip wall is nothing but velocity is not equal to 0. So no slip wall is nothing but velocity is equal to 0. So when we have the viscous effects, so the layer will get stick to the wall. So basically that is called a thin viscous layer. So and the boundary layer, so in which you have high turbulence and momentum exchange between the wall and the fluid, and therefore, so initially at the wall we'll give zero boundary condition, let's say velocity value 0, and so whatever the intermediate points are there, so here, so these points, let's say, let us give numbering, so 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. So basically starting from 23 to 40, so 23 to 40, so they are called the internal points or the interior grid point. So there the values of the flow properties will change. Okay. So here we have seen for the structured mesh for the internal aerodynamics or the internal flow. So here for the internal flow also we can divide into subdomains. So how we will actually see this. So let's say we have here. So here we have some hot blocks. Okay. So inside the pipe, so let's say we have the hot element. So how do we do actually? So we have to separately divide this into different blocks. So here, since this is a circular entity, you can go for unstructured mesh here. Here, since it is a regular entity, so here you can divide into domains like this. So here we can go for structured mesh. Okay. Here again you'll go for unstructured. Okay. So why actually? So for why we go for unstructured? So let's say this is block 1. So this is 2, 3, 4, 5, 6, 7, 8. Let's say. So here block 1 and 8. So basically they are circular entity. So if you don't want to waste time for generating mesh, so people go for unstructured mesh where you can give point directly here. So here, everywhere, this surface, here, and generate the mesh, okay, directly. So since in these blocks, so let's say second and third, so we have a square entity, so where the geometry is regular and we can perform. So even in the second block, what happened? We are divided into subdomains, so which is of 1, 2, 3. In the third block also we are divided into subdomains 1, 2, 3. So by dividing these blocks, so we will create a proper structured mesh. Okay. So here you can see combination of structured and unstructured is there, structured is there, structured and unstructured is there. So this combination is possible, and we are divided into multi blocks. So basically this is the concept behind the multi blocks and the structured and unstructured mesh, and we have seen the CH mesh for both internal and the let's say external flow, or let's say for the other problem which we have seen for stator and rotor. Okay, so in the next lecture, so we will see different types of schemes which we solve for this structured and unstructured mesh. So next we will see the Lax-Weintraub scheme. So where how do we use this finite difference method for this mesh and perform a numerical technique to solve the fluid dynamics problem. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.